We're starting in on sections 5.2, and in this section we're starting to talk about something called generally the rules or the laws of exponents. This is just looking at how exponents interact with other operations. So first off, I want to consider this example. If we have x squared times x cubed, if you want to think about what this will end up being, x squared is x times x. X cubed is x times x times x. And technically, I suppose if I'm doing a substitution, I should probably think of these as being in parentheses to begin with. But those parentheses I could ignore because this is multiplication both on the inside and on the outside of these parentheses. Just like there is an associative property of addition, there's also an associative property of multiplication, which allows me to just ignore those. So basically, I'm looking at this. And you can see, well, we have an easier way of writing that. This is x to the fifth. And you might be wondering, well, okay, there should be an easier way instead of having to go through these intermediate steps to go from x squared times x cubed to get to x to the fifth. Well, we have 2 of them, we have 3 of them, therefore we have a total of 5 of them. I'm just adding the 2 and the 3. So in general, what we say is when we have some number raised to an exponent, and then we take that same number raised to a possibly different exponent, what we can do is we just add those exponents. We get a to the r plus s. Alright, so let's do some examples. T to the fourth times t to the seventh. These have the same base, which means I can just add those exponents. 4 plus 7 is 11. This is equal to t to the 11th. Here we have a to the sixth times a to the first. Whenever we don't have an exponent, you can pretend there is a 1 there, and that allows us to use this property without really any changes. And we have the same base. A to the sixth times a to the first is a to the seventh. If we do that again, multiply it by a to the fourth, we get a to the 11th. On this one, now this is m cubed, this is m to the fifth, and this is n to the ninth. You'll notice that this 5 and this 3, these are kind of, these are not raised to that exponent. This is a 5 times m cubed times 3 times m to the fifth times 2 times n to the ninth. And not only do we have an associative property of multiplication, we also have a commutative property of multiplication, which means I can move these things around. I can take the 5, the 3, and the 2 and move them all to the front of this particular expression. I can play a shell game here. 5 times 3 is 15. Multiply that by 2, we get 30. M to the fifth times m cubed times m to the fifth. Well, that's m to the 8th, using the property that we just saw up there. And then n to the 9th, this is not the same base as these two, so I can't kind of push those together. This is a very very similar feel to combining like terms, but it's not quite the same thing. Keep in mind we're doing multiplication here. If I had something like n to the fourth plus n to the fifth, this is not equal to n to the ninth in general. This is not the same thing. This is not the rule we're looking at. But if I said n to the fourth times n to the fifth, this would be equal to n to the ninth. Do you see the issue? The difference here is if we're multiplying these together, we can add the exponents. If we're adding them together, that way does not work. So let's just look back at the general rule up here. You can see there is multiplication between the a to the r and the a to the s. It does require us to be multiplication.